Hello, my name is Arthur. I'm a PhD student at Huawei Paris Research Center and MinParis PSL University. Let me introduce you to ImPosing, Implicit Pose Encoding for efficient visual localization. We developed solutions for the image-based localization problem. This task consists in determining the camera position and orientation from which an image has been captured in an already known environment. We focus on driving scenarios where the area of interest covers several kilometers. The most common solution to address large-scale localization is to use image retrieval algorithms. The idea is to summarize the visual content in the image into a single vector, named global image descriptor. Before deployment, the descriptor of all previously collected images is computed and stored into the reference database. Then, during navigation, we extract the descriptor of the newly captured query image and search the nearest neighbors in the database. Finally, we can compute a coarse localization estimate by averaging the camera pose of the top-ranked images. Another option to solve this large-scale localization problem is absolute pose regression. The entire task is handled end-to-end by a deep neural network which takes the image as input and outputs the camera pose. These pose regressors are trained in a supervised way specifically for each scene. During navigation, a single forward pass on the network is sufficient to obtain a localization estimate. Retrieval methods need to store the database in memory during navigation. When lots of data have been captured, it can represent a massive amount of storage for the embedded device. Post-regression avoids this problem by memorizing the map into neural network weights during training, but direct regression approaches present a low accuracy, especially in large maps. The main contribution of our paper is to propose an implicit map representation for the large-scale visual localization task. We replace the image retrieval database by a MLP that takes a camera pose as input and outputs a global image descriptor. As a result, we are no longer limited to the finite set of observed images, but rather can evaluate any position in the map. At the same time, we preserve a very compact memory footprint. The proposed framework, named ImPosing, uses two separate neural networks, the pose encoder and the image encoder, which extracts a descriptor from an image. We learn a scene-specific descriptor space with a metric learning formulation. We train both networks jointly with reference images and camera poses. While pose regression models entangle features extraction and map memorization in a single model, we use two separate entities, resulting in a more accurate localization process. During navigation, we obtain a camera pose estimate with an iterative process. First, the descriptor of the query image is computed. Then, we compute the reference descriptors of a set of initial poses and compare them with the query image descriptor. High similarities indicate that the image has been captured close to the evaluated pose. By sampling new candidates close to the previous high scores, we can iteratively convert to the actual camera pose, which is computed by averaging the top candidates. We compared our proposal to state-of-the-art image retrieval and pose regression models on a wide variety of maps captured in different countries, with extreme weather variations and different training data quantity regimes. ImPosing performs better than pose regression in all the maps and outperforms image retrieval 7 times out of 9, while preserving a storage requirement of 20 megabytes thanks to the implicit map representation. You can see some localization examples here. Reference images are represented in gray, ground truth vehicle positions in green, and predicted camera poses in red.